Over the long years of teaching, I've noticed that the same gravitational field questions come up over and over again. In this video, I want to give you a method for how to approach all the variations of this question. Welcome along once again, physics fans. This is the second in my short series of videos about gravitational fields. If you want to get a deeper insight into just what gravitational field strength is, check out this video. Let's start then with an extremely quick recap. Here we have a 1 kilogram mass which is being moved away from the surface of Mars. You can clearly see that as you increase the separation, the strength of the gravitational field drops off rapidly. It is, after all, an inverse square law. We will now introduce the recently discovered twin of Mars and run our 1 kilogram mass along a line connecting the centre of masses of the two planets. The unit mass will be experiencing two forces, one from each of the masses of the planets, and we can treat these two forces independently. And because the forces are, well, forces and therefore vectors, we can just add them up to get a resultant. There is a point somewhere in the middle where the two forces are exactly equal and opposite, and therefore at this point there is no resultant gravitational field and hence no gravitational field strength, at least a resultant one. If we could put the unit mass at this point and providing it was stationary, then it would carry on being stationary because there is in fact no force acting on it. For Mars and Mars's twin, it's probably pretty obvious that this point is going to be midway between the two planets. But what happens if the masses are not equal? Where's the 0 point then? Imagine two planets of mass m and 4m separated by a distance d. We might be asked something like, how far away from M is the point where the two gravitational field strengths are equal? Or in other words, what is the size of R1? The gravitational field from the mass M is going to be gm over R1 squared. And the gravitational field of the second mass is going to be g4m over R2 squared. And of course, these two will be equal. We can now immediately do some cancelling out, so goodbye g's and goodbye m's. Our next step will be to cross multiply and take the square roots of everything, which leads us to, in this case, R2 equals 2 R1. We're well on the way now. Now we can also say, and fairly obviously, that the big distance d equals R1 plus R2. Remember, we're after the distance R1, so let's substitute in for R2, knowing as we do that R2 is equal to 2 lots of R1, and so this leads us to d equals 2R1 plus R1, which of course means that d equals 3R1, and therefore the distance R1, the distance of m to the 0 point, is d over 3, in other words, a third of the way across. There are many variations of this question, of course, but ultimately you will create two formulas, one for each of the gravitational field strengths, set them equal, and enjoy some algebra. I hope this little video was useful to you and that you will consider subscribing and liking each and every one of my videos. Bye for now.